Okay, so today we are doing 10.3. So let me share my screen so you guys can see the guided notes. We are finally at long last talking about exponential functions. So part one is graphing exponential functions. So in this section, we are interested in functions in the form f of x equals b to the x, where b is greater than 0. A function in this form is called an exponential function. So then we kind of have a formal definition there. And we are first interested in looking at the graphs of exponential functions. In order to graph exponential functions, we use the same technique that we would use to graph other types of functions, which is just to plug in points and then graph them, right? So you choose some x values, you choose some y values, you find some coordinate pairs, and then you go ahead and graph. So we have a nice little coordinate plane here. I'm gonna go ahead and zoom in so we can see it nice and big. Okay, and first off, we're gonna graph f of x equals 2 to the x. So again, what I am going to do is I'm going to go ahead and make a little table of x and y values, right? And I know that f of x equals y equals, what is our first function? 2 to the x. So let's pick some x values. I'm going to pick -1, -2, 0, 1, 2, and maybe 3, I guess, just for fun. Okay, and then my y values I know are going to be 2 to the x. So I'm going to have 2 to the -1, which is equal to 1/2. Fun reminder of exponent rules. 2 to the -2 is going to be equal to 1 over 2 squared, which is equal to 1/4. Anything to the 0 power, 2 to the 0 is equal to 1. And then I have 2 to the 1, which is going to be equal to 2. 2 squared, which is going to be equal to 4, and 2 cubed, which is going to be equal to 8. So let's look at my points. I have -1, 1/2, -2, 1/4. That one's a little bit hard to get to. 0, 1, 1, 2, 2, 4, and 3, 8, which is somewhere up there. So I can see that my graph is going to kind of curve up through like that. And that is my graph of f of x equals 2 to the x. Okay, and now I want you guys to go ahead and try to graph f of x equals 3 to the x on your own, okay? So pick some points, the same ones are probably fine, -1, -2, 0, 1, 2, 3. And by probably, I mean those points are fine, so use those points. And then kind of do the same thing and see if you get a similar graph, which, spoiler alert, you should get the same graph. Not the exact same, but very similar, kind of going up like that. So try that one on your own, and then together we are going to graph y equals 1/2 to the x. Okay, so x, y, which we know is going to be equal f of x equals y equals 1/2 to the x. Okay, so this one's going to be a little bit trickier, but again, I'm going to pick my same x values, -2, -1, 0, 1, 2, and 3. And then I know, again, y is going to be equal to 1/2 to the x. So I'm going to have 1/2 to the -2. So think about that as, okay, that is going to be 1 over 1/2 squared, right? Because we want to make our negative exponent positive by tossing it in the denominator. So that's going to be equal to 1 over 1/4. And then 1 divided by 1/4 is the same thing as 1 times 4 over 1, right? Well, dividing is the same as multiplying by the reciprocal. So we get equals 4. So our -2 point is going to be -2, 4. Then we have 1/2 to the -1. I don't know why my 1/2 turned out so weirdly there. So we're going to do the same thing, right? So we want to make our exponent positive. So we're going to toss that 1/2 in the denominator. So we're going to get 1 over 1/2. And then we know that this is 1 divided by 1/2, another way to think about it. And dividing is the same thing as multiplying by the reciprocal. So that's going to be 1 times 2 over 1, which is equal to 2. All right, then we have 1/2 to the 0, anything to the 0 is 1. Then we have 1/2 to the 1, anything to the 1 power is itself. Then we have 1/2 squared, which is equal to 1/2 times 1/2, which is equal to 1 over 4. And then we have 1/2 cubed, which is equal to 1/2 times 1/2 times 1/2, which is equal to 1/8. Okay, so I have my points and I'm going to go ahead and graph them. So I'm going to get -2, 4, -1, 2, 0, 1, 1, 1/2, 2, 1/4, 3, 1/8. I cannot get 1/8 on this graph. But as you can see, our general pattern is kind of going through like this. So this would be our graph of y equals 1/2 to the x, okay? And now I want you to try and see if you can graph y equals 1/3 to the x on your own, okay? So graphing exponential functions, very, very similar to what we've been doing in terms of graphing. Like you just literally pick some points and then you go ahead and graph said points. Sorry, my Apple Pencil is being weird, so I need to stop and then reshare. And then also I'm going to reset this. Okay, part 2, solving equations in the form b to the x equals b to the y. So we have this thing called uniqueness of b to the x, which I'm actually going to bold because it's like a definition theorem type thing. It seems important and worthy of bold text. So let b be greater than 0 and b does not equal 1. Then b to the x is equal to b to the y is the same thing as b to the x is equivalent to x equals y. So it's saying that basically if your bases are the same, like you have something to the x equals something to the y, you can just rewrite that as x is equal to y. Okay, so we have some example problems of this. So first up, we have 2 to the x is equal to the 16. And we know that we can only use this uniqueness theorem when we have b to the x equals b to the y. So that means we have to have some base b, which is the same in both cases. So if we're looking at this equation, we can see that our base b is 2. Okay, so then if we want to be able to set x equal to y, we need the base of the right side of our equation here to be equal to 2. So we have to think, can we write 16 in terms of 2 to the power of something? Okay, well, 2 squared is 4, 2 cubed is 8, 2 to the 4th power is 16, so we can. So we know that this is an equivalent statement to 2 to the x is equal to 2 to the 4th. Okay, and now we have that same base b, 2 and 2. So b to the x equals b to the y means that x equals 4. Just like that. Okay, let's do another example. So we have 9 to the x is equal to 27. So same thing. We want to look at this and see, okay, can we write 27 as a power of 9? Well, 9 squared right off the bat is 81. So the answer to that is no. But if we're looking at this, we can think to ourselves, okay, 9 and 27, like those numbers seem like they're related. And the answer is they are, because they are both powers of 3. So instead of 9, we could write this as 3 squared to the x is equal to 3 cubed, in which case our base is both 3, right? And then when we have a power to a power, we multiply. So we could rewrite this as 3 to the 2x equals 3 cubed. And then we have the same base and we can apply our uniqueness theorem and we get 2x is equal to 3. So x is equal to 3 halves. So we get x equals 3 halves. Okay, and then last but not least, we have 4 to the x plus 3 equals 8 to the x. Okay, so again, 4 and 8, can we write 8 in terms of 4? Well, 4 squared is 16, so no. But 4 and 8, again, seem to be related, and the answer is they are. And they are, we could write them both as powers of 2. So 4 I can rewrite as 2 squared to the x plus 3 is equal to 8 is the same thing as 2 cubed to the x. And then again, power to a power means we can multiply. So we'll have 2 to the 2 times x plus 3 is equal to 2 to the 3x. So 2 to the 2x plus 6 equals 2 to the 3x, same base, so we can apply our uniqueness theorem and we get 2x plus 6 equals 3x. So I'm going to subtract 2x the other side and I'm going to get 6 is equal to x. And my answer then is going to be 6. Okay. So that's exciting, woohoo. Different way of solving new types of problems, okay? And the one perhaps obvious problem with the above technique is that it will not work if you are unable to rewrite each side of the equation as powers of a common base. Thankfully, we will soon be able to bypass this and solve equations such as 4 equals 3 to the x when we learn later about logs. Okay, so like, you know, in all of these problems, we were able to rewrite each problem so that we had that same base b. But if we look at a problem like 4 equals 3 to the x, like 4 and 3, they don't have much in common. Like I can't write 4 as a power of 3, I can't write 3 as a power of 4, like I'm stuck for now until we learn about logs. Anyway, part 3, solving problems modeled by exponential equations. So interest rates on loans is one of the biggest applications of exponential functions. So we have an equation, and basically what these types of problems come down to is correctly entering things into your calculator, because these aren't the type of calculations that you would do by hand, okay? So we know the exponential function defined by a equals p to the 1 over r over n to the nt models the dollars a, so the dollars accrued, which is a, after investment of p dollars at an annual interest rate of r compounded n times for t years. So there's a lot of variables going on, but in these problems, you will be given a value for every variable except for the one variable that you're trying to solve for. So it's kind of just a matter of keeping track of these things, okay? So, example, find the amount owed at the end of 5 years if $1,600 is loaned at a rate of 9% compounded monthly. So, let's start defining our variables. So P, we know, is the investment. And so in this case, the investment was $1,600. Okay, or loan. Investment or loan, same thing. So investment or loan. It can be either, and in this case, it's a loan. So P is equal to 1,600, which is the amount of the loan. R, we know is going to be equal to the interest rate. And this time we know the interest rate is 9%, which we are going to write as a decimal of 0.09. N is equal to the number of times the interest is compounded in a year. And so since we are told that we are compounded monthly, our N value is going to be equal to 12 because there are 12 months in a year. If it had been weekly, then our N would have been 52 because there are 52 weeks in a year. If it had been daily, our N would have been 365 because there are 365 days in most years. Can't forget about leap years. Okay, so in this case, monthly, so N is equal to 12. And then our last value is T, which is the amount of time for the loan, the duration of the loan. In this case, we know that that's going to be 5 years. Okay, so we have all of the variables except for A, which is the amount of money owed or accrued, okay? So accrued basically just means like collected. So that could be money that you owe, money that you earn, just the amount of money that's there, okay? So we are going to know that A is equal to P, 1,600, times 1 plus R over N, so 0.09 over 12, to the NT, so 12 times 5. Okay, and then you should go ahead and enter this in your calculator, and the answer that you should get is approximately $2,505.09. Okay, so if you didn't get that, you typed something in wrong. So practice doing that until you get this answer. All right, next up, this problem was actually randomly in the textbook right after Ella Rose told me that she could find Chernobyl on the snap map in like 1 minute. So this one's for you, Ella Rose. As a result of the Chernobyl nuclear incident, radioactive debris was carried through the atmosphere. One immediate concern was the impact debris had on the milk supply. Like, this problem is straight out of the textbook, I swear to God. But like, the immediate concern of Chernobyl was milk supply. I don't even like milk. I feel like there's just so many more immediate concerns after a giant nuclear explosion. Anyway, I digress. The percent Y of radioactive raw milk after T days is estimated by Y is equal to 100 times 2.7 to the negative 0.1 T. I have no idea if that's scientifically correct. It would be kind of hilarious if someone had spent time writing a function to model the radioactivity of milk, but I can't guarantee that this is scientifically accurate. Estimate the expected percent of radioactive material in the milk after 30 days. So again, these types of problems are coming down to like, what variable are you solving for? So we are given 30 days, so that's going to be our t. So we're going to plug in 30 for t. Y equals 100 times 2.7 to the negative 0.1 times 30. Plug it into your calculator, and the answer that you should get is 5.08. Okay, so, or actually you should get like 0.05, 08, etc. But then we want to make that a percentage, so we're going to move our decimal twice, which is equal to roughly 5% of radioactive material in milk after Chernobyl, or 30 days after Chernobyl. The more you know. Never say that, you know, math isn't everywhere, because, you know, it is. Anyway, so that is it for 10.3. Thank you for watching, and have fun with the math line.